Now, wonder if I can play this. Maybe not. Let's see if this plays. I plays. So, hold on. So far, we've talked about coils. We've talked about evaluating the properties of, let's say, a specimen or a material, right? Conductivity, permeability, increasing conductivity, increasing permeability, and things like that, right? What else can we do? I mean, what else do you think this coil system that we talked about, producing eddy currents, can detect in a specimen?
Specimen.
Any kind of material or specimen. So this is what we
means conductive.
Conductive material, yes. Conductive, or let's say permeable. Now this is what we saw before. Now, let's say, let's say it's measuring now certain conductivity or permeability.
Mm-hmm.
Now what happens? It does a defect.
Oh, there is a cut.
There's a cut or a crack or
there's
anomaly. Or,
yeah.
What do you think is going to happen to this eddy current?
So there is a cut for the sum of the eddy current.
Cut means what? What do you?
I mean, it got I said there was a loop.
Yes.
There was a current flowing.
So you think
now it got cut. Open circuited for partially.
So it will.
Or current cannot take that route anymore.
Okay. Because current has to go somewhere, no?
Yes.
So, and that's right. So this is what we saw before, circular. But let's see, if you have a crack, then this current will kind of maneuver around this crack or find an alternative path.
Shortest,
yeah, exactly. And you could have something inclusion, here. And again, a different way. As you said, this loop is, as you said, cut.
Yeah.
As you see here.
Yeah.
Right? And then
so there is a modification to the eddy current path.
Yes. So then, if you're inspecting material, ideally, let's say you have a metal,
with no defect,
and your business is selling this metal, right? And you don't want any defects. That means we can use.
So I manufactured it. Before giving it to the customer, I wanted to test and ensure that this is good.
Yes, quality assurance, right? Then you should be able to use a coil system like this to perform that quality assurance, right? And evaluate the material. What is this, Boby? We've done this before.
You have done some bridges.
Yes, a bridge. So it is.
This also looks like a bridge.
It is a bridge.
So what is this test coil?
Okay, so
it's the same search coil that you were saying.
This is a simple but effective method of kind of detecting a crack, for example.
Oh, okay.
Right? So you could have your specimen here.
Mm-hmm.
Now, initially, let's see how a fresh, nice, clean, polished specimen. Okay? And then you use your coil system, you get your eddy currents, you get some value, and there'll be some current flowing in this circuit. Correct? Now this is a, let's say, a perfect or ideal material.
Yeah.
Now there will be some current flowing in this circuit. You can then play around with this impedance value and make this output 0. Okay? Now, if you remove this material and bring in another material with some crack or defect, now
for a different value, it will get balanced.
We get balanced. Right? So then we'll get some output here.
Or these bridge elements can be fixed. We can look at the unbalanced output also.
So you're saying, So you're having, we have all these 3 fixed, and then we just look at this. Yes, that is also correct. Yes.
And this Z1, Z2, Z3, these are represented using resistors, but I think at least one of them will not be resistor.
Yeah, that's true.
Otherwise, this bridge cannot be balanced.
Yes, I think that's why they put Z here, no?
Yeah. That is true.
Yeah.
But it should be represented using, I think, that square box.
Yes.
Because it says Z.
Something like this, no?
Yeah, correct.
Yeah, correct. Yes. But it's just a kind of simple and effective method, though.
So for the bridge to get balance, Z1, Z2 should be equal to, or
no, Z1 and Z3 should be equal, no?
No, the opposite terms, no? Z1 let's call this as the Z4.
This one.
Yeah. Then Z4 should be equal to Z2, Z3. Can't see fully from.
Yeah. Yes. Yeah. So this idea should be boxes.
Yeah.
Correct. But the idea is just you null the instrument.
Yeah.
Right. And then if you have a crack, you.
But usually it is not the nulling. No? Nulling is for explanation. It could be okay. But usually people will look at the unbalanced voltage itself.
You're saying leaving 3 the same and then just
probably with no object, you will balance and make almost null.
Yes.
Any object comes with fault will give an output.
Yes. Any object with a fault.
Yeah.
Yes. True. Yeah. Generally, yes. Now, we have already talked about 3 different variables, right? Conductivity, coability, and liftoff.
What are these lines?
Now we're talking about cracks. Now, we talk about the problems with the eddy current, right? Is that we have too many factors affecting the test, right? Temperature, vibrations, applied stressors, internal, external, electrical interference. So, another method, now, when you are looking at the output, let's say, and let's say that specimen or material has had a crack or has a crack. But if you look at the output, that crack could be masked within a lot of different frequencies.
So what is x-axis here?
X-axis here, good point. I'm looking at, let's say, different frequencies.
Okay.
Right? So
the same object.
Maybe amplitude there.
Same object?
Same object.
Okay.
Right? And you might have a lot of different frequencies within that same object that are due to all these other factors, right? So before you saw that bridge, but we can also probably think of using some kind of filtering to pinpoint the crack. So what I'm trying to say is you see, you understand better. Right?
Yeah.
So let's say you're looking at, filters, kind of analyzing the frequencies, okay? Let's say you're looking at only very low frequencies. Your output might look like this.
Okay.
Okay?
This excitation is very low.
Yes.
Okay.
And then your crack could be somewhere here. There's no way you know where the crack is. Right? Now, let's say you are only looking at, so basically you're filtering now, and before you were looking at only very low frequencies. But let's say now you're looking at very low and low frequencies. So you're kind of increasing the cutoff frequency, right? Then you might see that, okay.
This is not excitation frequency, no. I think what you meant is you have a test object, you are scanning like this.
Yes, this is scan, and then that could have many different frequencies, no?
Yes. I know, in between I made a mistake. I said is it the excitation frequency?
Sorry, I totally missed it.
Yeah.
No. So okay, maybe here.
Yeah.
I should actually explain that. No. So some object, and then you have your coil system.
Yeah.
You're actually scanning this.
Yes.
Right. So you're looking at here, like this, all these different places.
So each point you are getting some output.
Yeah.
If it's going beyond some threshold, you will say there is a fault.
Normally, yes.
Yeah.
Right. Yeah. But in general, this is what the output would look like.
Okay. Yeah.
Right?
Got it.
Then your crack.
Yeah.
Is kind of.
There could be faults due to various
things, temperatures, pressures, things like that. Yeah. So then rather than depending on, let's say, a bridge or something, yeah, we are thinking, okay, why can you use some filters? Let's do some filtering.
So this measured output from the inductor or from the coil,
Yes.
is now filtered.
Yes. Yes. The measured output is filtered. Yes. So let's say you initially look at very low frequencies, we can't see anything. Now you're increasing, you're saying, okay, let's look at low end, very low frequency. I mean, this is a very simple way of explanation, but I think students will understand what I mean. Now, okay, now it's a bit better than this, right? You can see some peaks here, but again, you don't know, right? I mean, this could be the crack, this could be the crack, this could be the crack.
Correct.
Then, let's say you increase your bandwidth a little bit more, right? You have your intermediate frequencies. Now, you can see you have a few frequencies, but the amplitude is changing. The crack is becoming quite obvious now.
Yeah.
Right? But still, you have these other kind of peaks.
We may get confused.
Yes. So then you say, okay, you know what? I'm going to use a high pass circuit, very high frequencies only.
Mm-hmm.
Then you get rid of all the other frequencies. Okay. Your crack appears.
So essentially, some amount of signal processing can be done to capture what you are looking for.
Yes. So all this time, we did not talk about any signal processing. Right? We just focused on the output and how we can tweak the system to get the output that we want. But even if you do have an output that, let's say, it's not ideal, then you can do some signal processing to kind of analyze a bit more and evaluate the crack.
Got it.
Right? Just another example. All right.
You are back to the
yes. So now,
again.
Yes, now we are looking at cracks, right? We are not looking at conductivity or permeability. Again,
but it is like effective conductivity is changing.
Yes.
When you have a
yes, because you have a discontinuation.
Yeah.
Right.
Yeah.
So your effective yes, and that's what you see here, right?
Hmm.
What do you think? So this is again the impedance diagram, like
Correct.
XR. So and also we assume that, let's say, this is a non-ferromagnetic material. Right? Nu is close to 1, let's say. And here you can see there's a little, when there's a crack. So again, you're scanning with the lift off, right? When you scan this specimen, this basically shows the scanning of 3 materials with different depths.
Means the
crack.
fault is at different depth.
Yes, the crack, let's say, is like this. And then here, the crack increases.
Okay.
Right? The depth of the crack.
So it's a surface crack?
Yes. We're talking about a surface crack. Right? So shallow lines, shallow cracks, right? Well, as you said, they interrupt the flow of eddy currents, right? So the amplitude is quite small, right? So here, what you see here is this kind of thing here, right? Is quite small for a shallow crack because the interruption is very small. Now, for a deeper crack, this eddy current flow is interrupted more, right? So this kind of signal that you get here increases, and also it gets closer and closer to the actual conductivity, which is what you said, right? You just said the conductivity goes back.
It's effectively reducing,
right? And that's exactly what you see here, right? So this is the curve that we saw before.
Okay,
right? Now we are using the same material, and if you scan it, suddenly it will go down, and there'll be a little point here. But this point depends on how. This is for a deep crack. This is for a shallow crack, and this for deeper cracks, it's getting closer and closer to that conductivity curve. So these are cracks on the surface. What happens when you have cracks at the subsurface level?
If it is within the skin depth, so there will be some effect.
So what I'm saying is now, before we talked about surface crack, right? Yeah. Just for to make it clear for the students. This is a surface crack.
Yeah.
Now, subsurface means your crack is, let's say, somewhere here.
Yeah.
This interrupts the eddy current. Does this interrupt the eddy current?
It will interrupt provided if it is within the skin depth.
Aha.
If it is below skin depth, you will not see.
Right. And why do you think this is now here? A and B is for subsurface cracks. C, it kind of goes this way. Now this is for a deep subsurface, and this is for a shallow. So basically, this amplitude also is high for a shallow, as you said, because it's within probably that depth of penetration.
Correct.
And here it's much smaller because maybe as you go deeper, that signal
Effective
is less.
So in the first diagram, A, B, C, C is for?
C is for subsurface.
Okay.
This is for surface.
Okay.
And this is subsurface.
So to some extent, we can even say whether it's a surface crack or subsurface crack.
Yes. Now, if it's a subsurface crack, then
you cannot see it.
Yes. Then but I think you still can't sell your product.
Yeah. And we'll have to send that away.
Yes. Yeah. Because there's a weakness, kind of weak points now inside that.
So then it makes sense, this non-destructive testing. I mean, you are seeing even the fault which is below the surface.
Yes.
Without opening it.
Yes. Otherwise, if you had to open everything, you had to throw everything. Yeah. Okay.